Welcome to the Problems Channel Season 3, Episode 18, the episode which I titled A Parabolic Motion with the Acceleration Parallel to the Y-Axis, because in this episode we will solve a problem that deals with precisely this type of motion. But before we deep dive into the underlying physics and mathematics of this problem, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from working with the material that we present on this channel is for you to go to the homepage of this channel, and at the top of that page in the channel's trailer section, find the episode titled The Problems Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. If you have any questions, then by all means do ask. The best way to ask your question is to find an episode that is of interest to you and use the comment section under that episode, and I will do my best to find the time to answer all of your questions. And of course, I want to extend my deepest gratitude to all the current supporters and the current subscribers of our channel. In the physics problem S3E18, we're told that a point is executing a two-space motion over a horns-up parabola, y equal to k times x squared, where k is a strictly positive real number, and the motion of that point in the parent plane is unfolding in such a way that the overall acceleration vector, a, of that point remains parallel to the y-axis at all times, where y and x are the traditional coordinates of the moving point in the Cartesian orthogonal coordinate system. The objective in this problem is to recover the shapes of the normal and tangential accelerations as the functions of time. And perhaps surprisingly to some, in such problems on kinematics of a single point, there is actually very little physics in such problems, because these problems revolve around the rudimentary differential geometry in disguise, which means that the more things you know about differential geometry, the higher are the chances of your success on the endeavor of taking kinematics in the course of theoretical physics. And such problems are actually indicative answers to the questions that I see a lot on Quora, for example, where young students ask, I want to do theoretical physics, but I'm not that good, or I think that I'm not that good at mathematics. Well, there is only one correct answer to that question, and it is the following: get better at mathematics, because back in my time, for example, such problems were good conversation starters for the verbal face-to-face in real-time examination, which was the format for all the exams in mathematics and physics back in my time. And the overall expectation was that you are supposed to or expected to slay this problem inside of 5 minutes with all the snap, crackle, and pop. Going into such problems, you are expected to know at the minimum everything that relates to the radius vector of the moving point, everything that is related to the velocity vector of the moving point, and the following facts about the acceleration vector of the moving point. In this case, the motion is not that complicated. It unfolds not in 3 space, but in 2 space. And in this case, in terms of the parameter called parameter S, which is the arc length traveled by the point so far, you're expected to know that the normal acceleration, I'll designate it with AN, is equal to the square of the velocity divided by R, where R is the radius of curvature of the given curve or of the given shape of trajectory where the point is at that moment. And as a vector, the normal acceleration always points towards that center of curvature or into the side where the curve is concave. And as a vector quantity and as overall magnitude, the normal acceleration characterizes or keeps track of the change of velocity's direction. Next, you're supposed to know that the tangential, I'll designate it with a tau, the tangential acceleration is equal to the second time derivative of the arc length traveled. I'll use the traditional notation where dot on top of a magnitude designates the first time derivative. Two dots designate the second time derivative of the quantity that is symbolized in this particular case. And you are expected to know that the velocity by absolute value, of course, the tangential acceleration as a vector is tangent to the trajectory at the point at the moment of time, and such an acceleration characterizes or keeps track of the change of the velocity's vector magnitude, not the direction, but magnitude. Tangential acceleration, magnitude, normal acceleration, direction. The velocity by absolute value is expressed in terms of the arc length traveled so far as the first time derivative, and in this case you will write it down as x dot squared for the x component plus y dot squared for the y component. Lastly, r for the radius of curvature of the given trajectory at the point where the point that is executing the motion over that trajectory is located. You are expected to know that this radius of curvature has the following shape: s dot cubed divided by x dot times y dot second derivative minus second derivative over x times the first derivative over y. Again, like I said before, all of this material is nothing else but a rudimentary differential geometry in disguise. Before we jump into the underlying computations, I would like to remark in passing that when the shape of the trajectory is given in the Cartesian coordinate system, whether that coordinate system is orthogonal or not, it is possible to write down the expressions for the normal and the tangential accelerations without the reliance on the radius of curvature r, but these expressions are somewhat cumbersome, but they only involve, the benefit here is that they only involve the first and the second derivatives of the x and y components of the corresponding trajectory. But in this case, it is illustrative and demonstrative to plow the solution path precisely through the radius of curvature, and to that end, we will do just about the only thing that we can do, because the only thing that we're given is the shape of the trajectory. So how do we spin it creatively into submission in order to answer the question that is posed in this problem? Well, we differentiate both sides of the given equation of the trajectory over time once, and I will use the dot notation for the derivative with respect to time. In other words, differentiating both sides of this equation over time once, we obtain y dot is equal to 2kx times x dot. This is differentiating the given equation of the trajectory over time once, and this is what happens when we differentiate the same equation over time twice. We will have y second derivative, y dot dot is equal to 2kx dot squared plus 2 kx times x dot dot second derivative over the x component, but we now go back to our statement of the problem and we convert, as we explained in the previous episodes, the verbal statement into actionable mathematics. If the acceleration vector of the moving point remains parallel to the y-axis at all times, then from here it follows that the contribution of the acceleration along the x-axis is 0, x dot dot is equal to 0. And that means that this term in the expression vanishes, and the only thing that we have left is the following: y dot dot is equal to 2k x dot squared. But that also means if this is true, then the only contribution to the acceleration is brought in by what? By the motion along the y-axis. It means that y dot dot is equal to a, and a is a given quantity, and we extract two units of information from this single equation alone. First, we instantly deduce that the first derivative of x over time is given by the square root of a over 2k. Game over. We know this is a function of time. And if we're given this equation, y dot dot is equal to a, from here it follows that dy dot over dt is equal to a. From here it follows that dy dot is equal a times dt. Integrating both sides of this equation from 0, let's say we agree that initially the y component of the velocity was 0. For simplification purposes, to y dot, and on the right we integrate from 0 to times t. So what do we have here as a result? As a result, we have y dot is equal to a times t, and voila, we have our two expressions. We have the expression for the first derivative of the y component as the function of time, and we have our expression for the first derivative of the x component as the function of time. Once the expressions for the first derivatives of the x and y components of the moving point as the functions of time are known, it becomes possible to write down the expression for the rate of change of the length of the arc traveled by the point so far as the function of time. That is, we simply take the first derivative of x, the first derivative of y, square them, sum them, and extract the square root from that sum, and we thus have s dot is equal to square root of a over 2k plus a squared times t squared. And in order to make this expression somewhat more digestible, we can carry out the expression a over 2k from under the square root. So we will have a over 2k times square root of what? 1 will remain as the first summand, plus we took out one copy of a square will be reduced to just a, and 2k will have to come into the denominator. 2k a t square is our expression for the first derivative of the arc length traveled so far. And once we know that expression, we can also write down the expression for the radius of the curvature of the given trajectory at a given point. That is precisely because the acceleration vector of the moving point remains parallel to the y-axis at all times. We remember that the contribution of that acceleration along the x-axis vanishes, which means that in the corresponding formula for the curvature of the trajectory at a given point, the second derivative of x dot dot, vanishes, and the shape for this radius of curvature becomes especially pleasant. It is s dot cubed over the first derivative of x times the second derivative of y, and we know all the expressions over here. Let us write down the cube of the first derivative of the arc length traveled as follows: square root of a over 2k times a over 2k times cube root of 1 plus 2k a t squared, like so, times the reciprocal of the first derivative of x over time, and is this expression over here, square root of 2k over a, times the reciprocal of the second derivative of y over time, and this is simply 1 over a. And what do we see? The square root and the square root cancel out. One copy of a and one copy of a cancel out. And as the function of time, our radius of curvature emerges as the following expression: 1 over 2k times the cube root of 1 plus 2k a t squared. And once we have that expression on the books, we can write down the expression for the normal acceleration of our point as a function of time. Namely, according to the formula that we wrote down over here earlier for the normal acceleration of our moving point, an as the function of time, we have the square of the first derivative of the arc length traveled. It will be this expression, a over 2k times 1 plus 2k a t squared divided by the radius of curvature, which is this expression. This will be again one copy of this expression, complete expression, at squared times the square root of the whole thing, 1 plus 2k a t squared, and what used to be in the denominator goes into the numerator, times 2k. So what do we see? 2k and 2k cancel each other out. One copy and one copy cancels out. The only things that survive is the acceleration and this horrible looking square root. As such, for the normal acceleration an of our moving point as a function of time, we have the following expression: a over square root of 1 plus 2k a t squared. This is the first result we obtained. We wrote it down, and now we can move on to the tangential acceleration of the moving point as the function of time, which is simply the first derivative of the first derivative of the arc length traveled so far. That is, the tangential acceleration of the moving point is the second derivative of the arc length traveled so far. And since we already have the expression for the first derivative of the arc length traveled so far, we see that the tangential acceleration of the point in this case will be the first derivative of the first derivative of the arc length traveled so far, and we know how to compute derivatives. And in general, in many pleasant cases, in other words, for finite compositions of elementary functions, that task can be completely automated with the so-called shunting yard algorithm, or an algorithm in computer science that was put together by a theoretical physicist by training, Dijkstra. But today and here and now we do it the old-fashioned way, by hand. We know how to compute derivatives. As such, we take our expression for the first time derivative of the arc length traveled so far, shown over here, and write down the expression for its second derivative as follows. The constant real number known as the square root of a over 2k is factored out. In the numerator, we will have 4kat, 4kat, and in the denominator, we will have 2 times square root of 1 plus 2kat squared, to be neat. And now we can brush it up a little bit, make it more digestible. Look at this, 2 in the denominator and 2 in the numerator cancel out. We have 2. And now we take 2k and a and bring it under the square root as what? 4k squared and a squared. 4 in the denominator and 2 in the numerator cancel out. K squared over k becomes k. The independent variable t we factor out. T times, and what do we have left? Well, what we will have left is the following. 2k, a squared times a is cubed. 2k a cubed over 1 plus 2k a t squared. This is our expression for the second derivative of the arc length travel. So in a sense, this is our expression for the tangential acceleration as the function of time. Let's put it down over here to make sure that we see it. T times square root of 2ka cubed in the numerator over 1 plus 2kat squared in the denominator. And amazingly enough, are we done? No, we are not done yet. And the reason why we are not done yet is a quite sad state of affairs when, in the process of solving this or that problem in theoretical physics, we quite often go through an amazing set of convoluted mathematical extortions, if you will. And at the end of this battle, let's say we won that battle somehow miraculously, we managed to derive what we think is an answer. Most students rush forward to the next problem or onto bigger and better things, and most of the time most students fail to do what is required of all of hard science people. We step back, we take a 1,000-yard view, let's say, at our problem, as Carl Gauss used to say, and we're supposed to ask ourselves the following question: does our solution make any sense to begin with? And sometimes we can answer that question, and we can do the so-called sanity check. And in our case, what will be the sanity check? Well, one thing we can do in this problem is the following. We went through mild mathematical contortions, let's say, but they were still contortions nonetheless. It was some mathematical magic. But let's say we put together the square of the normal acceleration and the square of the tangential acceleration. We sum these two squares together. Will we obtain the value of the acceleration in this problem A or not? Now, if that sanity check squares, does it mean that we solved the problem correctly? Well, not really. It sort of indicates that we did not mess up too badly, because maybe we somehow miraculously made an even number of mistakes that cancel each other out. But on the other hand, or conversely, if our sanity check does not square, if we compute the sum of two squares and the result is not precisely a, then we know for sure we mess things up somewhere, and then we enter the infinite loop. Search for the problem, think about how to fix it, try again, and go in that, run over that loop over and over again. So here, blindly and bravely, we do precisely that. We write down the expression for the square of the normal acceleration and the square of the tangential acceleration. So what do we have? We will have a squared in the numerator and 1 plus 2 kat squared in the denominator, plus, what do we have here? 2k a cubed times t squared over 1 plus 2k a t squared. Do the things look good for our hero? Look at this. A squared and a cubed. We can factor out one copy of a squared. What we will have left in the numerator, denominator is the same. 1 plus 2k, one copy of a, 2k a t squared over 1 plus 2k a t squared. Cancel. The result is a squared. So according to our favorite Pythagorean theorem, the sum of squares of the normal and of the tangential accelerations comes out to be exactly what we expect it to be, the acceleration a, which is a given in this problem. So this is the indication that we did not mess up during the solution of this problem too badly. We have reasonable foundations for a hope that we solve this problem correctly. And that's the one thing that you're expected to do. The other thing that you are expected to do is a somewhat of a high wire balancing act, even though I will suggest it to you. I myself, in my college exam taking career, in real time, face to face, sparring with the mature professional who has been doing this for many years, did not do too many times, but several times I was able to do it. And here is the thing: show an initiative, try to walk an extra mile and see if it is possible to at least pluck some low-hanging proofs. Now, in most of the problems that are given in, for example, my time, real-time verbal face-to-face examination, these problems were wound up so tight that you barely had the time to solve the problem and do what is asked of you. Going above and beyond what was, like I said, a high wire balancing act. It was not as simple and as straightforward. It is challenging. You have to be very confident in your abilities to do that, because in the, again, real-time face-to-face examination format, you are nervous, you are not sure if you made a mistake or not, and if you make a step forward and that step forward is not correct, you will not produce a good impression. Your grade will be hanging in the balance of the step. But sometimes in some problems, if you can handle the pressure, it is possible to pick and collect some low-hanging fruit in a given problem. And what are the low-hanging fruit over here? Well, remember, we wrote down the expressions for, what was it, for the first derivative of x. It came out to be, if I'm not mistaken, a over 2k. And you can suggest to your examiner that you can compute the law of motion over the x component if you integrate both sides. So in general, you will have it as x of t will be x0 plus square root of a over 2k times t as a function of time. So this will be the initial coordinate along the x-axis at time 0. What was our expression for y dot? It was a t, if I'm not wrong. So integrating this equation, both sides of this equation, you can suggest to your examiner that you can write down the expression for the y component as a function of time. Here, of course, you will be integrating from, you will have to integrate what from y0 to y, so your expression will be y0 plus at squared over 2 as a function of time. And what is missing over here? Well, remember that initially we said that y dot 0 is equal to 0. That's why the term that you expect to be here is missing. So if it's not the case, if the initial velocity along the y-axis is not 0, then you will have an extra term over here, which will read what? Plus y dot 0 times t, for example. You can explain this situation to your examiner. And the other thing is the following. You know the angle between, let's say, at this point, what should I do? How should I draw it? Let's do it this way. If we take our acceleration vector that points parallel to the y-axis at all times, and let's say we have our tangential acceleration that runs somehow this way. This is the A tangential. And then the normal acceleration, we'll designate it with the blue somehow. Let's pretend that this is the normal acceleration. And then the vector sum somehow balances out to come out to the red vector. So this will be your normal acceleration. Look at this. This angle right here is the angle technically between what the acceleration vector and the velocity vector, give or take. If the point accelerates, so then the velocity will point in the same way. If not, then the velocity will point the opposite way. So the angle between the velocity vector and the acceleration vector will be pi minus this angle theta. And what can you say about this angle theta? Well, this angle theta will be, the angle theta as a function of time will be evidently an arctan of what? The normal acceleration divided by tangential acceleration. You can compute this on the fly, so to speak. Let's see if we can do it. Arctan of what? If we divide our normal acceleration by the tangential acceleration, what will we have? We will have the following. One, let's see, let's do it over here. We will have a over square root, and then we'll have to divide it by what? Square root of the whole thing. Here it will be t, square root of 2ka times a. If I didn't make any mistakes on the fly, cancel, cancel. So the square roots, notice that the square roots will cancel out. So this will be the arctan of what? It will be an interesting function, 1 over square root of 2ka times 1 over t. This is how the angle between this angle right here, essentially this is the angle between the tangential acceleration vector and the y-axis effectively. This is what you definitely can tell to your examiner. This is the case. This will be the vector. You can draw this diagram, and you can show that you can carry out this computation again in real time. Even if you're nervous, you can make a mistake here and there. Usually the professor who will examine you, if he sees the initiative, he or she sees the initiative, then they will be lenient if you make some arithmetic typos or mistakes. But fundamentally, this is the extra work that you are expected to carry out. Now, this is it for the problem S3P4, and we will move on to a new challenge next. Our next challenge will be a problem in computer science numbered as S3CS4, Season 3, Computer Science Problem number 4. And in this problem, we're told that a given input array of length n is logically partitioned into two sub-arrays. Let's say a left sub-array of length n1 and a right sub-array of length n2, such that n1 plus n2 is equal to n, the entire length of the input array. And the objective of this computer science problem is the following: creatively, with the emphasis on the word creatively, swap in place these two sub-arrays in such a way that the sub-array that was on the left side of the input is taken in order into the right side of the output array, and the right sub-array on the input is taken into the left sub-array on the output. I showed this particular configuration of the input on the top, the intended output on the bottom. Here we have 5 blue circles, let's say, of the input are located on the left, or logically on the left, and we have 7 yellow squares are located logically on the right. Let's say this is the right sub-array. The objective here is to creatively swap these two sub-arrays, or let's say discrete line segments, in such a way that the 5 blue circles that were on the left in the input go into the right of the output in such a way that their order remains the same. If these 5 circles were on the left side of the input in the order A, B, C, D, E, then they have to go into the output on the right side in the same order, A, B, C, D, E. Likewise, the 7 yellow squares that were on the right in the input have to percolate to the left of the output in the same order. In other words, the yellow squares in the output array is supposed to be in the order 1, 2, 3, 4, 5, 6, 7 in the same order. And the in-place requirement means that the space complexity of this algorithm, whatever you come up with, has to be big O of 1. You cannot allocate any more substantial memory than you have to. That means that practically you only have a room for a smidgen of frame variables in your algorithm, where you can perhaps swap a small number of elements, such as, for example, 2 elements. But this is about it. And as a fair warning and as a heads up, if the only thing that you can come up with for the solution of this problem is to reverse the order of the left sub-array, reverse the order of the right sub-array, and then reverse the order of the entire array, then again, as a fair warning and a heads up, this is not the intended solution. For that solution, you get an F. In the creativity department, you need to try harder, think, precisely because, as we declared in the title of this, in the banner of this channel, we're looking for out of the box solution for technical problems in mathematics, theoretical physics, and computer science. As such, in this particular problem, we're looking for an out of the box solution. And as a hint, as the first hint for those who want to take this problem and take it to a successful solution, the one way to do it is to think about the underlying mathematics. That's the hint number 1. If that hint is not enough, then the hint number 2 is that the good old planar Euclidean middle school geometry may be helpful. Now, this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the computer science problem, S3CS4.